Hi, everybody. Folks will continue to trickle in, I think, but we've got a quorum. Anyway, hi, I'm Andy Ross, for those who don't know me. I'm a software engineer at Google. I'm on the Chrome OS team where I work on audio DSPs and occasionally sound open firmware. I've been a Zephyr developer for a good while before that, sort of at large, primarily in the kernel, doing scheduler and timer subsystems. I've done some of the arch layers in like extensive, again for the audio DSPs, that sort of thing, or some of the early x86, 64 stuff. And I'm here to talk about actually none of that. We're going to talk about ARM context switching. Oh, am I not loud enough? Oh, that's much better. Okay, yes. So we're going to talk about context switching on ARM, which is not really what I've done in the past, but yeah, it's a lot of fun. So the background on this actually starts out just about a year ago, about 11 months back. This very nice man, Jacob Bigningo, has a embedded software consultancy out there and a blog, and in a absolute masterstroke of marketing, managed to embarrass Zephyr really badly. He released a RTOS benchmark suite and ported thread metric to a bunch of systems, published benchmarks, and you can see I snipped one out there, and there we are at about, I think you can't even read it on the slide. It says about 11% of what PX5 is getting, and maybe a fifth of ThreadX and free RTOS. That's the cooperative context switching benchmark right there. That's what we're going to be talking mostly about today. Yeah, we just did really, really badly. And needless to say, it took a little bit before we noticed suddenly there was a big kerfuffle on Discord. I was trying to keep my head down, to be perfectly honest. I'm not really involved in most of this slide. But very rapidly, of course, you see a number like that, something is wrong, and clearly it was a configuration issue, and that on the device he was using, which is, it's an ARM Cortex-M board, just like we all tend to see, we had user space enabled by default. We had the MPU enabled by default, MPU, stack guard, things like that, all of which tend to produce overhead. We aren't particularly performant in our MPU usage. I'll talk about that a little bit later. And so, clearly we're not this bad. So very rapidly, folks got in touch with him again. I was not involved. He published another revisit, a couple weeks later, showing that, oh yeah, we were not nearly as bad as the first time. We were still in last place though, and that's a little embarrassing considering we've always sort of considered ourselves a high performance RTOS. And so, well, what went wrong? And that started a kind of a change in zeitgeist, change in feel in the Zephyr kernel community. And folks started looking seriously at little micro optimizations, and there were lots that were done in the coming weeks. Peter Mitzis at Intel did most of the heavy lifting on this, doing things like changing we committed a version of the thread metric benchmark, changing the default scheduler backend for that benchmark to use the multi-cube scheduler, which was had been there forever. It is very slightly faster. Didn't ever seem like it was useful. It has a limit to the number of priorities you need. That sort of thing that you get, that sort of thing. And we got much better, and I think we had pulled kind of broadly even with everybody else. But obviously it changes the way you think about things. It changes the things that we all tend to think are important, and it also opens up the possibility of thinking about rewrites of the stuff that have been annoying you forever. And this is obviously on ARM Cortex-M, and it's all well and good to go into the generic kernel and fix things in the kernel that are needlessly slow or inefficient or just had been forgotten. A lot of these changes were things like reordering functions so you can inline them better, that sort of thing. But there's a whole arch layer below that, and the one that we've got is good, it's stable, it's been with us forever. Obviously everybody's aware of ARM Cortex-M. It needs no real introduction, right? It's the pervasively dominant architecture in the industry. It may not be the sexiest thing in the world, but like whatever it is, 67% of all of our board targets, you do twister build -all on Hello World and just count which ones are Cortex-M, and that's what you get. So just to really, really quickly refresh folks, and I will say here, in previous years I've given speeches, and it's always been speeches. I've given talks at these things, and it's usually a tutorial level thing about IPC or the scheduler. And I'm always careful to point out that yes, I'm a kernel and Arch developer. We're not going to talk about assembly language. Not this time. That said, though, I mark this as an intermediate talk. This is the assembly that's going to be presented is all in the spirit of look how simple this really actually is. It's not too scary, but that being said, there is some kind of weird and subtle stuff coming up. So buckle up. I'm going to go as fast as I can. I do tend to wander. Bottom line is, really quickly, ARM Cortex-M is ARM. It is descended from, the original Acorn architecture from way back in the 80s. That means it's a in-order RISC. It's pretty straightforward load store architecture. It has 16 registers, not 32, whatever. Nothing particularly weird, but it is among the weirder RISC architectures out there. Some things that you do need to remember are like the program counter. PC is a general purpose register. It's R15. You can read to it. You can write to it. We'll talk about that in a little bit. It makes some things easy and it makes some things hard. There's also, interestingly, an IP register, which is the R12 or R13 or R12, which is not an instruction pointer. I don't remember what IP stands for, but it's kind of odd that the architecture decided on both names. It does have some weird instructions that you'll need to take a look at. So LDM and STM are the ones that most folks who are familiar with Cortex-M assembly are going to see. ARM has had these instructions forever, but they basically are load and store instructions that load a whole array of values into an array of registers out of one pointer. It's a microcoded instruction. It's not risky at all. It does have the advantage on these particular CPUs that the address generation step, like a loader, the LDR STR instruction on ARM is usually a 2-cycle instruction. It needs to compute the address and then issue the load in a following cycle. It doesn't, these aren't big enough to have a parallel issue kind of thing. And those can share the same address generation with literally like 12 or 13 register reads all at once. We'll talk about that in a bit. It has auto increment and decrement modes, which are like push and pop, right? That's is the way you understand that. Again, this is not risky at all, but it's something you do tend to see in the assembly, and it's something you can exploit when you really need to worry about performance. It also has some really weird stuff we'll talk about later. The IT instruction or IT family of instructions is a conditional block. ARM historically had a conditional code in the beginning of every instruction, so that you could say, okay, well, if the last comparison was negative, you do or don't execute this instruction. Thumb or these particular devices inherited that, but it's a prefix instruction. So here's an instruction. Here are 4 subsequent instructions that can be conditioned on that one thing. And again, we'll talk about that in a bit. And then the big weird like oddity behind Cortex-M is that it is a thumb mode device. ARM historically, obviously, is a 32-bit instruction with very traditional looking RISC. At some points, I think it's around ARM v3 or ARM v4, they found themselves in the embedded market and decided that they were having to compete with all of these older CISC architectures, like x86 being one of them, that really beat them on instruction density, right? Like if you're really worried about spending ROM bytes on instructions, having smaller instructions is actually really valuable. And so they invented this 16-bit instruction encoding that was kind of a subset of the overall architecture. It limited most of the instructions to just 8 registers, just the prefix of 8 registers. It used a different ABI, so you would save them all. It actually looked a lot like x86, to be perfectly honest. And you had some other instructions you could use to shuffle between the full register set if you needed to. Cortex-M uses thumb. It is not exactly the same. It's an extension of thumb 2 really on most of them, except for the ARM v6 Cortex-M 0. Which we're not porting on this thing, so we're not going to talk too much about that. And so everything becomes a little bit different. You've got a variable length encoding, instruction coding now, where it's like some are 16, some are 32-bit. Really, it starts to look, I got to be honest, a lot like x86. And then the final bit down at the bottom is that unlike almost every other RISC architecture out there, exceptions and interrupts on this device are going to push a block onto the stack. This is designed for OS-less or minimal OS firmware integrations, so it doesn't want you to have to write a whole lot of switch code on your own, which doesn't do us any good. We're an operating system. That's what we do. And then the final bit of architectural notion that you kind of need to remember with ARM is that they invented this thing called PendSV on Cortex-M. So SVC on ARM is a software interrupt, right? It's just, it's a service call, right? You issue the instruction and it traps to a exception, and then you can handle that doing whatever you want. Well, they also have this thing called PendSV, which is exactly the same thing, but it exists at the lowest priority of the system, which is every other interrupt is going to interrupt PendSV. So that the idea is that you flag this thing, and that will cause the interrupt to happen as soon as it's available. So if you happen to be in thread mode, you're just running on doing regular stuff, it'll just, bang, it'll be your service call right there. It'll act like a system call, act like a trap to the operating system. If you happen to be up in a interrupt handler at the top of the stack, it essentially just waits. It says, all right, great, I'm going to run this code for you, but only once you're done with this interrupt. So now the interrupt can go and do things like change the state of the system, and in particular, change the thread that it wants to be running. And then when you come back down, just before you re-enter thread mode, you run your special PendSV interrupt handler, and that becomes your context switch. This is the kind of the model that the CPU was designed to do. I'll be honest, I've always hated it. The first reason is just pure hygiene, right? Like entering and exiting an entire exception trap, which is going to push 8 words onto the stack, run the code, which has to swizzle those 8 words to change what it's going to do, and then pop them all back off the stack at the end is just an awful lot of extra work to be doing for something like context switching, which really does need to be very fast. But it is also tripped over in the kernel, or has been tripped over in the kernel repeatedly. Because the problem is that when you made the decision in thread mode, you've taken a lock, you've entered the kernel, but you're still in thread mode, and you've said, great, I'm going to switch to this other thread. And so you change the kernel's internal bookkeeping of what thread it's running, the current thread pointer, to this new thread that you're going to run, and then you flag your PendSV and you're done, right? But no, because it's the lowest priority interrupt, you can then take another interrupt right now, like a timer interrupt. It's going to fire as soon as you release the lock. And that timer interrupt comes in and says, okay, well, great, well, who's the current thread? Well, there's 2 answers. One is there's the value of the current thread pointer that the kernel just updated, and there's also the thread that you actually interrupted, which has not switched yet. And so there are a bunch of bugs we've had traditionally in the kernel that we've had to work around, and we actually have a kconfig in our config swap non-atomic to flag exactly this misfeature. It's actually gotten better over time. At this point, it's really only needed by the time slicing subsystem. But as we would discover a bug, it would get wrapped under this kconfig so that we didn't need to carry the baggage around on other systems. And we've tripped over it repeatedly. It's been a couple years. Things have stabilized quite a bit. But again, this has just always been my personal pet peeve with this architecture. And so if this sounds kind of like I'm jumping in on this performance rush in order to chase a personal vendetta against ARM's context switching primitive, it's not entirely wrong. But nonetheless, we're going to take this seriously. If we're going to be serious about performance, let's be serious about performance. And then, and this is just getting it. I'm actually going to zoom through this because I don't think this is that useful, and I tend to go really, really long anyway. The older context switch primitives on ARM are really irreversibly tied to the Z-swap, the original context switch primitive we had. Z-swap, I had a whole slide just talking about the distinction here. Basically, Z-swap is the older version that requires the context switch talk directly to the scheduler to get the the thread to switch out of the kernel directly. Arch switch lets the kernel make that decision on your behalf and just gives you a place to store your outgoing switch handle and your incoming one from which you'll restore. Arch switch is required for SMP because obviously in SMP you have to make that decision atomically at the time of switch. You can't just go to a location in memory to get your next thread to run because another CPU might have stolen it at the same time. And there are, ARMv8m does allow for multiprocessing. I am no expert on the multiprocessing architecture on this, but nonetheless, we would like to be able to do that. So let's do that. It's also there's got a couple of oddball features. Custom swapped main has always been enabled, and the reason for that is that there's a separate handler mode versus thread mode. The ARM device has a banked stack pointer. And you need to get the system running on the right stack pointer before you can switch to the main thread, and so it's not the same thing as a cooperative context switch. Now it can be. I actually haven't fixed that one because I didn't want to remove any code in this pull request, but nonetheless, it's on its way out the door as soon as we can remove the older code. Likewise, config arch has custom thread abort. There are races versus pentest-v that require that. Don't ask me exactly what they are. I know that it was required. It's unclear to me why it really needs to be there. But again, those are both there, but they'll be going away soon. And both of those, if you look at the implementations, they're basically duplicates of logic that's already in the scheduler. And we would reliably break things. We would make changes to the scheduler that would break on ARM, and it would break on ARM because ARM had its own version of that code that we need to go and update. So it'd be good to get rid of this stuff. So let's get started. So we want to do a traditional context switch primitive for ARM, right? This is the desire. Well, let's first start out with just the hardware frame, right? So I snipped it out of the ISOREF, but you can look at the hardware frame on the side of the screen right there. And see what it looks like. There are oddities to it, some of which are very clever, some are not. One is that the CPU really actually only pushes 7 out of the 16 registers, the 8th register obviously being the stack part, which you recover from the thing that you pushed. And the reason for that is that registers 4 through 11 in the defined ABI for the platform are call save registers. If you've got a C function and you enter the C function, it must restore the state of R4 through 11 before it returns. And what makes this really clever is you can make your C function into your interrupt handler, right? You just call straight in, and you can rely on the compiler to issue spill and fill instructions for those remaining 8 registers. You don't actually need to have the hardware do anything on them. That's a good idea, and we're going to steal it later on. There's an alignment wart, which I think is more of a misdesign. Obviously, it's a 32-bit architecture. The stack pointer can be 32-bit aligned. You can point to anywhere in memory. The ABI, however, says that it's an 8-byte stack alignment required on entry to C functions. So what do you do if you've got an interrupt that happens when the stack is misaligned? Well, one answer is you actually just call the C function, almost nothing breaks. And we don't want to do that. You might have DSP code in the ISR or whatever. And so the ARM decision was actually that the hardware is going to handle this. It's actually configurable. There's a stack align bit you can set in a configuration register somewhere. But we set it. And so when you do take an exception, which is almost never, but you do take an exception on a misaligned stack, it's going to stuff an extra word in there. And you can tell that it did that because of a bit that it sets in the PSR, the XPSR there, which is the processor status register. Not great. It means that if we're going to be doing this with software, we need to be checking that extra bit every time and be prepared for these different alignments. A bigger wart, though, is that the PC, which is the return address in that chart, is not at the top of the stack. If you think about the way context switching works, is at the end of the process, you need to atomically jump to wherever the address that you were restoring to, and at the same time have restored every single register to whatever state it had been. And that's not really possible to do in just regular instructions because the address you're jumping to would itself need to be in a register, right? So like how do you figure that out? What you do is this pop PC mechanism where you can use the stack pointer, which you've aligned or which you've set up to just one word below where you want to go. You pull the PC off, and now the stack pointer points to where it wants to go. That doesn't work with this format because the PC is not at the top of the frame. So the very first thing I needed to do was just rearrange the words in memory so that to put the PC in the right spot. Nonetheless, this did work. And the final note is that this is still just only 7 of the registers. You still need to put the other registers somewhere. They have to be above this frame if you're going to be using the hardware stuff, right? Because otherwise the hardware return wouldn't see the right value. But then you've got this other register block at the bottom of your stack, which you then need to fix up with some extra code, so you end up having to stuff in a trampoline into your return address, which then pulls the right value out and does the restore. It was basically kind of a mess. It wasn't really any better than what we had. I stuffed a little note in the corner there. Is if we're really being serious, we really want to do this perfectly. What would make this perfect? What is our perfect stack frame format? And so let's try this one. And so we'll start with some quick principles, right? So the first thing is everything's going on the stack, right? The current context switching in ARM puts those call save registers into the thread pointer and the regular hardware stuff on the stack. And that's a little bit annoying if you're going to deal with that in software, because now you've got two pointers you need to deal with. You need extra instructions to set one of those pointers up, which is going to be some offset into the thread struct. If you can just pop everything off the stack linearly, that works a little bit better. Second principle is we want this to be inline. We want it to appear in a C context. We don't want this to be a block of assembly to which we need to jump. The simple reason is just that that jump is going to take an extra cycle, or more if it's a misdirected branch. We would like this to look as clean as possible. It doesn't need to be very big code, and the kernel doesn't actually have that many places where it really needs to context switch. I think there were 4 calls to reschedule, which is the primitive that we're actually inlining into in the kernel. In the entire kernel. So it's okay to duplicate this code a little bit, and we want to at least let it do that. And the bigger reason, though, is that we can steal that whole callee save register trick for ourselves, right? That, obviously the C context in which we're inlining this code is itself in a C function, or maybe that's inlined too, but somewhere up that stack within the compiler, we're in a C function that knows it was called from a context where it needs to save registers 4 through 11. We can rely on that. We'll just list them as clobbers in our own situation. That gives the compiler the freedom to say, well, maybe I don't need registers 4 through 11. Maybe I can just elide these. I'll never assign them. I'll never do with anything. The context switch then comes in and might replace them with any old garbage that it had on the stack, and it doesn't matter, right? And so that sounds like a great deal. Or alternatively, the compiler might have the freedom to be very smart about how to spill and fill those registers, more so than we would be if we had to just manually write them all out. And then the final bit is let's go backwards here. So remember that ARM has this LDM STM kind of architecture where you can actually just load a whole bunch of registers all at once. And it's easy enough to just kind of just read the ISA spec that, oh yeah, okay, you can do this all with 2 instructions. You can LDM R0-R14 or whatever it is, all at once, all the way up through the link register, and then one final instruction to pop PC. You ask, why do you have to have 2? Why can't you just do it in 1 instruction? That's just that's the way they did the instruction encoding. There is no single instruction that can be encoded to load all 16 registers. It's unfortunate, but oh well. Or 15 registers, you wouldn't load the stack pointer that way. So let's start with that. Let's come up with something that's going to look kind of like that. And you see that I snipped out a little bit of C code there. That is in fact what the switch frame looks like. It's not the actual code because I cheated. I didn't have enough space on the screen. So the R0 through R13 I wrote as an array. But that's it. So let's give it a shot. All right. So we're actually going to sit there. We're going to write some assembly, and it looks like this. Ta-da! One is, it's actually pretty small. So this is, and again, full disclosure, this is not exactly what you're going to see if you look at the pull request, because the pull request has if-defs for FPU registers and the PSP lim, the stack limit register, and it's got some C code above and below to handle user space, the MPU settings, all of which is fairly straightforward code. It just doesn't fit on a slide. But this is, in fact, this really is what's going to be generated for those high performance cases that we were talking about in the very first slide, where you're going to be wanting to be benchmarking cooperative multitasking. And I'm realizing I really should have found a laser pointer before I started this, but we're gonna look at this really, really quickly, right? Again, these are all fairly straightforward instructions. It's all simple stuff. And the nice thing is once you get it all together, it's really pretty straightforward. You see the very last 2 instructions are exactly what I just talked about. We're gonna pop all the registers except for PC, and then we're gonna pop PC right off the stack, and then at that point we're now running in our new frame. The ones immediately before that are there to set the APSR, the application PSR register, that's like your your comparison results and things like that. The PSR register is actually a big 32-bit register that has a bunch of pieces. We'll talk about this later. Not all of which can be written by software. The APSR is like the equivalent of an x86 flags. It's all fairly straightforward. The syntax for that MSR instruction is insane, and I don't know why they did it like that. But it's those NZVCVQ flags there are just telling you which flags of the APSR register would you like to write from the R2 register, which contains the source. There's no just way to say all of them, please. And that's it. And those 4 instructions there in that little bottom there, that is the resume path, right? Everything above that is either the store path or the little bit in the middle that's swapping the stack. The store path is a little bit more complicated, right? Because we need to move things around. We don't have all of the registers available. 2 of the registers you notice are dedicated to the 2 function arguments, switch to and switched from. And again, we've chosen R4 and R5 there specifically because those are clobbered registers. That gives the compiler the maximum freedom to deal with things. If we use R0 through R2, that forces the compiler, because it knows that it's been using those for scratches already, to spill them itself, which means we'd end up having to save them twice. So we basically arrange a block of, R6, 7, and 8 have the 3 words at the top. Then you notice we're just going to subtract 24 from stack pointer there. We're going to just skip the spots for saving whatever it is, R6 through R11. We're not going to save them because this is a cooperative context switch. We need space for them, right? Because you need space in this frame in case it was an interrupted frame that does need to restore all the registers. But we don't need to save them here because we can rely on the compiler already having done it for us because we're in this inline context. Then we push, R0 through R5. Those are all just conventional things. We do need to set APSR. You will note that 1 bit being set there. That is the thumb bit, and it's actually part of the EPSR register. The thumb bit is just a consistent pain point on this architecture. It's really inconsistent about whether or not it needs it to be there and whether or not it writes it itself. I didn't mention this earlier, but in thumb mode on a traditional ARM processor that supports both 32 and 16-bit encodings is the bottom bit of the PC. If you jump to an address that is divisible by two, then that is a traditional ARM instruction. If it has a 1 in the bottom bit, then it is a thumb instruction. The Cortex-M devices will panic, or not panic. They'll toss a usage error if you jump to an even valued PC. Which is why if anybody here ever accidentally pull out a function pointer and try to jump to it on an ARM processor, and you get the really helpful panic warning that it is an invalid use of the EPSR, that's why. The EPSR has been loaded with a value that has a 0 in that bit. And so before it even tries to do the instruction fetch, it's giving you this panic, which is why it's not giving you something that's sane like invalid PC value or something like that. And like I say, there's really very little else to it. You'll notice down at the bottom, there's a very traditional clobber list. We're clobbering, we're clobbering R6 through R11, R4, and R5 are our 2 input registers. There's a symbol label there for the end. And I will find, well, there's one more note here is that this is not Cortex-M0 compatible. This is an ARM v7 code. Again, those long variants where you're dealing with the high registers, anything from R9 and higher, or R8 and higher, tend to be thumb 2 instructions. Doing the same work on Cortex-M0 would just simply be a lot more code. I mean, it's not code you can't write. And on our existing, assembly layers, we've got if-defs around there all over the place, selecting between Cortex-M0 and Cortex-M4, well, ARM v7. And so I don't have it fixed yet. I think we probably will do it, but I think there's an argument that the very small systems are very likely to be space constrained. They'd probably prefer to keep with the PendSV architecture anyway. We'll talk about code size in a little bit. And then the final thing there is, I said this is perfect, and I think actually this is getting there. I mean, again, if you look at the number of instructions here, I believe is 17. There really is almost no wasted work here. There are no branches. I'm really pretty proud of this. There's nothing I can look at here that I think is really going to be that much improved by another scheme. And so I think we've done very, very well. The one thing I will note though is that where you see it pull out the PC value, which is the equals 3 label there, and then it has to add that thumb bit to it. Why can't you just have a constant that it would use? And the reason for that is that, well, the assembler is just not really up to that. The assembler can't give you a constant that has an actual address because it's the assembler. You don't know that until the linker. But what you could do is you could add to PC. PC is a general purpose register, right? You can say there is some magic number that will take the PC value that you see up at that thumb bit computation and then produce the address of 3 plus the thumb bit there. The reason you can't do that, however, is again, the assembler can't do it. And this is a specification work in the architecture that way back in the day, they specified the PC as being a 4-byte aligned address of the next instruction to be executed. Thumb instructions are 2-byte aligned. So if this happens to be aligned correctly, then you'll get the right answer. If it happens not, it's gonna align it down by 2 bytes and you'll be off by 1 instruction. I actually did kind of prototype. You could fix this post linkage. You could stuff a label in there to mark the instruction where you're going to do this, or the 2 instructions where you're going to jump to and where you're going to do it, and then use like a Python script and PyElf tools or something to. I made it work, but you know, I made it work in like a dummy situation, so I think it would work. But nonetheless, the savings would be 2 cycles, right? You would replace that one LDR instruction as 2 cycles, and the add, which is 1 cycle, with a single thing. But nonetheless, when you get to code of this size, 2 cycles matters. In fact, even in the benchmark that I'm dealing with, that I added to this PR, which is kind of trying to measure the minimum like round trip through swap. You know, using the Zephyr API though, not whiteboxing this code. It's set like 70 cycles on actual hardware to do the context switch. You know, 2 cycles out of 70 is a couple percent. That's, you know, it's probably worthwhile. All right. So anyway, ta-da! It's there. We're done. Right? Well, no. Okay. There's still more stuff to do, right? So we've got a perfect switch format that says nothing to do about what happens when you get an interrupt, right? Interrupts are still coming in on the hardware. They're still pushing the old frame. So the architecture decided on here is that this thing becomes the switch frame. We're just going to call it the switch frame. It's the frame we use for any suspended thread, right? If you've taken an interrupt, you leave the hardware frame in place. You don't need to fix anything up on entry to the interrupt or anything. Just call your ISR. Most of the time, right? It's a system call. It's, you know, you're going to be returning back into whoever called you to begin with. And so you don't need to do any swizzling. It's only when you're going to context switch on interrupt exit that you actually need to do something. And the way this works is that there's an interrupt exit hook that already exists in ISRs, you know, just generically in Zephyr, right? That's, you know, it's just part of our API requirements. And what they do is they change the link register, the return address for the very lowest level of the interrupt stack, so that when you're finally returning to thread mode, it actually jumps to this fix-up code. And the fix-up code then checks, do you need to return? There's some complexity with trust zone. If you've crossed a trust boundary, you need to return direct, or if you elevated, or excuse me, if you dropped in a trust boundary, you need to return directly, because you may not be able to read the stack of the thread that accepted. So there's a little bit of complexity there, but it's not that bad. And you see I've even thrown in the C code that is designed to do that. You see the thumb bits being set again. And so basically these are just doing swizzles of, you've got 2 big structs. One represents the switch format, one the hardware format. They do the rejiggering. You'll note that the implementation strategy of the 2 is entirely different. One is creating a temporary struct and then assigning it to memory. One is trying to be smarter about pulling the fields out in the right order so that you can write them back in. Believe it or not, I started out with the struct version thinking that was stupid and slow, but it was easy to write. And then I updated them to what looks like the hardware to switch format right there, which is much more intelligent. In the switch to switch version, it was actually generating worse code. So I think this is something I think we need to do some investigation on. I think some handwritten assembly for these steps would probably be a good idea. It's a little complicated because I mentioned earlier that alignment thing. The offset between the interrupted stack pointer and the actual resumed stack pointer of the process is going to be one of 2 different values. In fact, it's one of 4 different values, because you can, on an FPU system, you could have pushed the FPU values or not. And that means you've got to have those same, all of this needs to be generated 4 different times. And yeah, I don't know, I'm not super pleased with this yet, but the good news is that yes, this is slower, and it actually is. It's about like 18% slower on the interrupt exit path times for that context switch case, right? But the good news for that, or the good news, at least the explanation behind this, is that this only impacts interrupt exit, right? The interrupt latency, that is to say the time it takes to get into your ISR and do the really important thing that you need to do, is completely unaffected. We only deal with it on exit. And it only corresponds to the wake-up case, where you've taken in a hardware interrupt. Again, software interrupts are always going to go back to whoever interrupted you. Well, unless you're deliberately trying to do something that would cause a context switch, but you wouldn't in this case because you don't need dependency anymore. so it's like the wake-up case is like you've taken a hardware interrupt and it's produced network data or storage data or something like that for some thread, and you've woken up a higher priority thread and you're going to switch to that. And that's like the IO-bound interrupt case, and those tend strongly not to be performance cases. Just because if you're bound by interrupt latency, trying to wake up and feed all of these high priority things, you probably are going to be like right at the edge of what the hardware is going to be able to do, to begin with. So I think we're probably okay here, but I can see arguments to the contrary. And this is an area where I think we do need to continue to do some looking. And so that's really it. And I think like I've presented like the core stuff that I think is the things that most people are going to want to take away. The rest is all stories. But they're important because they're the hard parts. They're the things that you realize that didn't quite work with the initial design, and you need to do some rethinking. So there's this category of ICI/IT instructions. I mentioned IT earlier, being that multi-instruction predication structure. We can issue this predication instruction, and then your next 4 instructions can be conditioned based on the test. Those. And I can see why ARM did this, and I'm not sure that it was the right decision. Those can all be interrupted midstream. That is to say, you've got this 4-instruction IT block, or like we just saw in the context switch, that 13-cycle long pop that we were doing at the end of the context switch. You can take an interrupt right in the middle of those things, and it will sit there and stop where it is, having only gotten 14 of the 12 of the 14 cycles or whatever completed, and then jump to your interrupt and then come back and restore it later on. It doesn't need that much state, right? Because there's not that much complexity to what it's doing. But it does need a couple of bits. Those bits are in the IPSR. Again, the PSR register is this 32-bit structure. Some of the bits correspond to different virtualized registers, not virtualized, these different named theoretically distinct registers. And critically, you cannot set those bits by software. We cannot, in a software context where we're going to do a software context switch to a thread that had been interrupted in the middle of one of these instructions, we can't set those bits. And if you think about it, that actually makes some sense, right? Because every instruction in principle can be one of these instructions. All of these instructions can be setting these bits just in the stream. You can't be writing software to write to those bits because the software that's going to write to those bits is already writing to those bits. So you would need some hardware mechanism to do that, and I think from the hardware designer's perspective, I think an exception return is as good as it gets. And I realize I forgot to point this out, but I got all the way through like working code and a submitted PR before I fully understood what the problem was here. Wilfred had been working on a similar arch switch thing, which had not gone away from the PendSV architecture. PendSV doesn't have this problem because PendSV is an exception, right? And Ethinwell had to kind of poke me a couple times, like, how exactly are you solving this problem? And I'm explaining that, oh, it's not a problem. It's going to take the exception right here, and it's just not even getting that this is a problem. So it took me a little while, but I did kind of eventually figure it out. And so the solution here, because we don't want to give up, I mean, like naively, right, you would have to give up this whole software context switch architecture. But the truth is, you don't need to, because you can detect when this happens. And it's really quite rare that you take an exception right in the middle of one of these instructions. It's not that rare, because they're actually very useful instructions. You see them all over the place. But it's certainly a very small fraction of the total number of interrupts you've taken. And interrupts, again, are a very small fraction of performance cases in real operating systems. And you can just check. You just look at the bits, and are any of them ones, right? Because thankfully, the specification does tell us that they write as 0 if you're going to start at the beginning of instruction. And we actually rely on that, right? When you start a new thread, you're creating one of these software frames, or you're creating one of these hardware frames in software, and you write zeros into those bits, and you know that it's then going to start at the beginning of whatever instruction you point at. There are no special rules, so therefore we can know that ones reflect midstream instruction failures. So we can test this. It's really, it's a 1-bit mask test, in the middle of the exception handler. And if found, It's not that bad. What we do is we swap the PC, the restore PC, with a trampoline, right? So it's going to restore back to that thread, but the thread is then immediately going to trap back into the operating system. So the question is, how do you get it to do that? And there's lots of ways to get a piece of software to trap. PendSV actually would be a perfectly good one. I chose the UDF. They gave us an undefined instruction trap as an instruction right there in the architecture. It's a little bit easier to manage than PendSV because PendSV has a very big handler already. So you enter into the trap. You do one quick address check to make sure that you trapped from the trampoline address and you don't have an actual undefined instruction. And then you take the actual restore PC that we got from the original exception and the actual PSR that we need to restore, the thing that we're trying to deal with in the first place, stuff those back into the hardware frame that was just pushed for us, and then just return, and it just works. And it actually works. I was amazed at this. Almost everything was now passing at this stage, and this was really pretty quick. And this takes us up to about I think March or maybe early April of last year. And the really hard problem, and this is actually mostly just a story of me just being completely stuck on a bug for what really turned out to be about 3.5, 4 months. And like all bugs, it was just a stupid thing. There's an FPU state bit that gets set in the PSR value, or in the LR, excuse me, the EXE return value in LR. And I had hand shifted the value and typed it in carefully and got it wrong. And it was sitting there and reporting that the FPU had been pushed when it was not. And the shocking thing is almost everything works, because one is most tests don't enable the FPU. That code was just not present in the OS for almost all the tests. What tests are using the FPU tend to be using the FPU, and therefore are going to be pushing their state when you take an interrupt. And so where it didn't work was a little bit difficult to detect. I mean, again, we were down to just a couple of platforms that would fail, turned out to be the ones with FPUs, and a couple of tests in those that would fail. Interestingly, ones that typically timer tests, anything that was doing a lot of sleeping or a lot of like wake-ups. And I couldn't get this, but eventually I saw it because it just looked like corruption. Again, invalid use of the EPSR, right? That kind of thing. It was pulling garbage off the stack, and why was garbage getting in the stack? And I started logging stack pointers, and eventually I caught the smoking gun. It was just dumb luck. I would come back to this, a couple hours every week and get it, and just completely fail. But eventually I caught the idle thread with the stack pointer that was way outside its stack. And then at that point, and we'll talk about this in the context of QEMU later. QEMU is actually deterministic on single core systems because we use iCount, and I'm not folks are familiar with QEMU, but it really saved my butt on a lot of these problems, precisely because you could catch it doing one bad thing one time and just keep hammering and just keep looking at it in the debugger until you got it. So what was actually turning out was happening was I already told you what was happening is we were assuming the FPU frame had been pushed when it hadn't. So the hardware would push 8 words and it would think it was pushing 32 more, and so then it would then pop all that off and you would start up above where you had been. It was a stack underrun, but even then it wasn't actually, because the FPU wasn't in use. It just thought the values were there. It wasn't actually writing anything, right? It wasn't clearing the stack. If it had done that, it would have been a lot easier to see. What it was doing was every time the idle thread would take an interrupt, it would drop a bomb of 8 words, kind of scattering up through memory. And which is why this was just so hard to tell, because a lot of, like, the idle thread didn't care. The idle thread will start up with will come back with a completely corrupt stack. It doesn't care because it's got almost no code in it. It's all just immediate mode stuff. And so, eventually it lands on top of something that's important, but that can be much, much later. Anyway, like I say, there's no real lesson there except keep at it. Eventually you'll figure it out. Eventually you'll just get lucky. So that's a good segue here. Let's look at lessons. We're getting towards the end here. I'm not wildly over time, actually. I'm fairly pleased. I deliberately left a bunch of stuff at the end to talk about if folks want me to continue, but if you're really sick of me or need to flee or or whatnot, we can do that. First lesson is just the Zephyr test suite is gold. We have an enormous test suite at this point. It's extremely slow. I mean, like, like building all the ARM Cortex-M tests is a little over 2 hours on my device, which is one of those 3990X, 64 core monsters from like 5 years ago. It's a little long in the tooth, but I've been so pleased with that machine. I love having it. But even on that thing, it's really quite slow. But nonetheless, it's going to find everything. And in particular, there is a time slicing variant of the syscall stress test, and it's, tests memprotect, syscalls, and then the time slicing variant. And what it does is just iteratively makes a whole bunch of system calls really, really fast out of a user space process, and then just time slices taking interrupts. And that just played hell with everything, and it was having a lot of trouble. Second lesson, I mentioned that already, persevere. You just keep at it. You will eventually find it. I think at this point we really are out of actual bugs. Third one is trust the hardware documentation. I touched on this earlier where Wilfred had to kind of point me at the misfeature where I had simply misunderstood stuff. But in fact, this particular, like the ARM v7m references, which is what I was, kind of like was the gold standard for everything I was writing to. It's documenting something that may not necessarily be the cleanest design in the world. A lot of the hardware is kind of confusing, but the reference manual was really good, and it's complete and it's correct, and I was really pretty pleased with it. So this may not be a big lesson to I think a lot of people who are more inclined to do things like trust documentation. I'm sort of a cowboy on that thing and tend to think everybody else is as careless as I am. It's really not true in this case. That was just a great document. It's a great reference to use. And the fourth one I mentioned too is just QEMU. It's not the sexy new world of like, Renode and all the fancy emulators out there. But it did everything I needed it to. It's built into the SDK. Everything works great. Including those ICIIT instructions that I talked about. QEMU actually does emulate the arrival of a interrupt in the middle of a completely emulated instruction. I don't know why, because there's no practical reason in an emulator you would want to do that. You should just treat the instruction atomically, right? Because you're not a cycle exact emulator. But clearly, at some point, one of the authors thought somebody like me was going to come along and want to actually test this stuff. And the very fact that I could make this happen sitting there in the emulator in a deterministic fashion was just really helpful. And to the extent that, like I say, we're at the stage now where I think really we've fixed everything in this, and this is all ready to go in. There are no actual bugs, and not one of them was unreproducible in emulation. Like there were some that were found first in hardware because some things are just glitchier than others. But everything, once I knew where to look, I could make it happen in QEMU. And the final one is just, it's nice to know that there's still space for this kind of work. AI is not taking this job anytime soon. It's just too weird and too strange. And the final note is, I didn't actually try. And if anybody does, get a AI-generated context layer that beats this, I don't really want to know. Just claim you wrote it. All right, but wait, this is all supposed to be about performance, right? And so the answer is about 8%, or at least that's on my devices. I've got a couple of STMicro Nucleo boards. Don't ask me to remember the product naming numbers for STMicro devices because I can't. And then I have an NXP Freedom board. And 8% is not bad, and I think that's going to push us up beyond what FreeRTOS and ThreadX are doing. I think Honest might have had some numbers early on in this pull request. It's actually gotten better since then, so I expect it to look pretty good. The micro numbers, it's more like 70%. If you look at that 17 instruction, like magnificent, perfect context switch thing. But the truth is, the rest of the system does dilute things, and there's still some low-hanging fruit for performance that I'm noticing in the scheduler. Arch switch, which is, and again, I didn't talk about the distinction between switch and swap, but Arch switch was written for SMP. It tends to look at locking as a fine-grained thing. when in uniprocessor situations, as long as you've got one lock, you know you've still got the lock. Everything is just recursive, and they all just stack on top of each other. So there are spots where I see we could kind of fix this up. I've got a few more slides that I could talk about performance issues, but I don't think those are super interesting. And then the interrupted switch case that I did mention, it is slower. I think we can do better than we're doing. I think we're probably never going to be quite as good. And finally, yeah, someone call Mr. Benigno. I think it's time for a retest. And finally, this is still in review. I was amused by the Milton Friedman quote because it just sounds like context switching, even though it's a libertarian nonsense. So you please review. It still does need a review. If you've got hardware and you're willing to run tests, Loic in particular has been really helpful on this. But you know, I'm like just one guy, and it would be really good to get this a little more, a little better exercised in the world of hardware. So yeah, so take a look at the PR. I do need to get these slides submitted so you guys can click on those links. And at this point, I think I'm gonna stop since I'm probably at time. I can go through the rest of I've got like 2 more slides, which just have notes that I pulled out of the rest of the slides knowing I was gonna go over long. If anybody has questions, just shout them out. That's probably better that I talk about what you want to talk about. Yeah.
Well, it's maybe not really a question, just some note. Like you said about performance deterioration is 18%, but only for the case when you do the context switch while returning from the interrupt. It's actually one of the most important benchmarks for an RTOS, which is the wake-up time of a thread in reaction to the external event.
Mm-hmm.
And it has very important uses, at least in our products. So just as an example, there's a whole world of ADCs without internal buffering, which give you an interrupt for every sample, and they do it like 4,000 times per second. And you have to read it over SPI every time they give you a sample.
And you can't do it out of the ISR?
And you cannot do it from the ISR in Zephyr because you cannot schedule SPI transactions from an ISR in Zephyr.
Is that true? Okay, well, so I'm thinking we don't want to fix that, but okay.
It's not our platform.
Right. So
maybe it's MCU dependent, but then I wasn't able.
okay, so basically, to repeat the question or the statement was, I'm wrong, and we really do care about this case. And I think you're probably right. I think there is absolutely space for that. I mean, I'm coming from a perspective of looking at this more as like a performance thing in the abstract. Where you look at, you know, what's going, like where are real systems going to spend all of their cycles? And context switching, cooperative context switching is something you can do at the, you know, even on these devices, you know, all the way up, like getting towards like 1 million context switches, you know, per second, right? Where you've got architectures that are inefficient but naive and simple, like, you know, read a byte, write a byte, read a byte, write a byte. Things like that, or even like, you know, even looking at like what like big core systems tend to spend their time doing. Like if you type, you know, West build on a Zephyr thing, it's going to go out, it's going to run CMake, CMake's going to run all of these different little processes to test all things. Well, it'll pull it out of the cache, which is also just opening up repetitive files. There's like dozens and hundreds and probably thousands of processes that all get started, all of which need to context switch between each other. So it's very easy to get stuck in a situation like that. Whereas the interrupt case, again, like I say, is less of an issue, or at least less of a performance issue. But no, I mean, you know, if those are significant things, then yeah, get into the PR and set me straight. Like I said, I think we're probably never going to beat the existing code on that. Just because of the need for that swizzling of the thing. But there are other options too. You could imagine a hybrid structure where you essentially do the opposite. You store it pickled in hardware format and then swizzle to the context switch thing, and you could change between those with a kconfig. You could do that actually almost right now, just because both of those the transition functions are already present. It's just a question of which one you want to call in which order. The other option is just you could stick with PentSV. Is just continue to use the same architecture. The structure of the pull request as it exists right now is that it's not removing any of the existing code, right? Exactly. There's a pre-existing kconfig called use switch, and that's just what I'm using as a switch. And on Cortex-M0 devices, it's still exercised because I haven't written the assembly for the ARM v6 stuff. So you certainly wouldn't see that disappearing in the immediate term. I mean, I don't know exactly what the consensus would be different for like how many versions should we leave the old value in, but if there are significant requirements and this doesn't meet them, let's get a test in there and take a look. So yeah.
Good question. And when you enable use switch in the PR now, can this be not triggered at all?
Yeah, in fact, the handler doesn't even get built. Okay. But yeah.
What's a good way to measure the performance of the thing?
Well, so there's two answers. One is thread metric is the sort of new hotness benchmark that we added in the wake of this Benigno fiasco. And I don't love it. It's very seemingly free RTOS centric. It like in particular the context switch or the cooperative switch test is doing it by setting priorities of threads directly, which in Zephyr has never been a performance case and was not really like that's just we were not fast at that. So again, Peter at Intel had to do a lot of work to try to make that case fast versus doing something like giving a semaphore or some other kind of more natural IPC mechanism in Zephyr that would have performed better. The other one is that in the PR, I wrote a couple of micro benchmarks for, and those are the ones from which I'm citing those numbers, which were intended to try to measure just the switch code with a little more discrimination. And those tend to give bigger numbers, like it's 18% on the 18% loss on that particular test. Thread metric is lower, but I don't remember what it was saying. And the reason it's just thread metric is just more diluted by the rest of the system. So yeah.
One more question for me. If you compare FreeCOS with the old Zephyr implementation before your changes, why is FreeCOS faster in the benchmarks? I presume it doesn't use like this custom form of it.
No, it's using PendSV. It's just smaller and tighter, and we've got a lot of extra features that have added complexity over the years. I mean, the big one, obviously, in the disaster originally was just user space was enabled. That's doing a ton of stuff. We're calling C functions out of the PendSV handler when we really shouldn't be. It should just be swizzling the registers in the stack frame. There's certainly space to do a much better PendSV handler. Again, my personal proclivities say that that's a terrible idea because it's burned me repeatedly in the kernel. But yeah, no, there's lots of space where we could improve.